my name is Ayşe Sarıcıoğlu. Today, me and my friends going to present about a topic that combines two different disciplines, biology and technology. The title of our presentation is Neuromorphic Computing Systems. The reason we choose this topic is because that we are truly inspired by how nature influences human inventions. Since the beginning of a human history, nature has always been a powerful source for inspiration, for new ideas. Today, technology is not only used to make a daily life easier, but it's also beginning to mimic the structure and behavior of living organisms. Devices are becoming more intelligent, more efficient, and even more human-like. This is especially interesting when we consider how the human brain or animal nervous systems process information so quickly and effectively. One of the best examples of this is the structure of neurons and neural network they form. These networks, whether primitive or complex, offer an excellent model for computer architecture. In biological terms, neurons are stimulated by impulses, and these signals are transmitted to the brain, where the information is processed and responded to. These systems work with incredibly low energy. For example, the human brain can perform billions of operations using only a few watts. This brings us to the key idea: how can we transfer this biological communication and efficiency into computer systems? In this presentation and our report, we focused on neuromorphic computing systems, how they can be adapted into computers, the role of neural networks and chips, and their advantages and limitations.
Hello everyone, my name is Ecem Altınbaş. In this part of the presentation, I will talk about the background of the neuromorphic computing. The idea that computers could think like human beings has been around since early 20th centuries. Alan Turing's Turing test was one of the first serious steps in this direction. But back then, computers worked with the von Neumann architectures, where the processor and memory were separate, and data was processed one step at a time. In contrast, the human brain processed data in parallel, which gives it a huge advantage in certain tests. To close this gap, artificial neural networks were developed. The first model was created by McCulloch and Pitts. And in 1957, Frank Rosenblatt introduced the perceptron. But since it couldn't learn in multiple layers, progress in this field slowed down for a while. In the 1980s, Carver Mead started neuromorphic computing by building brain-like systems using analog circuits. In the 1990s, devices were created that mimicked human eye and ear. These early models provide that machines could imitate the brain's functions. Later, with the use both of the analog and digital systems, large-scale neural simulations became possible. In 2014, IBM introduced its True North chip, and in 2017, Intel launched Loihi. Then, in 2024, Intel released HoloPoint, a powerful neuromorphic computer with 1.15 billion artificial neurons and 127 billion synapses. Today, the idea of the machines working like the human brain is no longer science fiction. It's becoming reality.
Hello, my name is Batuhan. I will talk about the literature review today. SNS simulates brain dynamics using neural models like IF, it means integrate and fire model, LIF, leaky integrate and fire model, and SRM, spike response model. And analog inputs are converted into spike trains, often using values like +1 and -1. They can be organized as feed-forward or recurrent networks and learn using techniques such as STDP, spike timing dependent plasticity. And we can talk about SNS offer real-time adaptability, energy efficiency, and biological plausibility. They are applied in image recognition, sentiment, and gesture detection, biomedical signal processing like EEG and ECG, and motion estimation by analyzing spike patterns to understand speed and direction. And we can talk about the applications of literature review. On the hardware side, companies like IBM, Intel, and the Spinnaker project have developed neuromorphic chips such as Turing-North, Loifi, and HoloPoint, which simulates over 1.15 billion neurons. Their systems use astronomical communication via AER protocol and energy-efficient memory like CMOS circuits and embedded RAM. In the conclusion, we can talk about chips, and we already talked about the Loihi and HelloPoint. In conclusion, SNS are a promising step towards more brain-like AI, but there's still a long way to go before we fully match the human brain. Thank you for the listening. That's all.
Hello, I'm Dilara Nurardiç, and next we're going to talk about potential vulnerabilities. The first one is biological complexity, because the way human brain works is not simple. We have 86 billion neurons with adaptive parallel synapses that work together. And mimicking this type of complexity is extremely difficult with technology. Another issue I'd like to talk about is immature algorithms, because SNNs are still in experimental phase now, not truly done yet. And training methods like STDPs are not yet competitive with backpropagation. The next issue is hardware integration issues, because it is difficult to interface with CPUs and GPUs. And because of that, we need custom chip manufacturing, like Turing-North or Loihi, and they are costly and not scalable. Another issue is programming difficulty, because these type of systems require spike-based asynchronous thinking, and they lack mature development tools. And because of that, developers can't build or test these type of neuromorphic applications. Another issue is energy efficiency. It's task dependent. It's not actually really energy efficient. And because of that, energy in actually excellent in low data tasks like recognition of audio, but they are poor in high throughput like NLPs. Another issue is limited generalization, because human-like thinking, human-like learning is when we have few examples and we learn it and then we generalize it. But computers can't do that. They can't mimic these type of systems. And because of that, they struggle with flexibilities, and tasks like complex reasoning, they can't do that. Another issue is lack of industry adoption, because other than major tech companies, there are really low investments in this field. And because of that, there are few skilled developers and limited market demand. And that was it. Thank you for listening.
Hi, I am Dilay Bayrak, and this part of the presentation I will talk about how we can improve neuromorphic computing system. First, let's look at learning algorithms STTP, spike timing dependent plasticity. It's commonly used in neuromorphic models. It struggles with complex tasks like image recognition or language understanding. To improve this, we can make STTP more modular so it adapts to different use cases. Adding stability mechanisms like homeostasis can also help prevent overfitting, and by combining STP with deeper context-aware models, we can make learning much more efficient. Next is software development. A major problem right now is the lack of user-friendly tools. Most neuromorphic platforms are hard to use for beginners. To solve this, we need to better SDKs, graphical interfaces, and interactive environments that support learning and collaboration. Educational materials should also be expanded and integrated into academic programs. Finally, on the hardware side, neuromorphic chips are expensive and hard to scale. Open source hardware and hybrid architectures mixing traditional and neuromorphic systems could reduce cost. Partnerships between industry and academia can also support wider adoption. In short, improving algorithms, tools, and hardware will make neuromorphic computing more powerful and accessible. Thank you.
As a conclusion, it's complex to develop technology designed to resemble the brain. This modeling, which has been developed since the past and has evolved towards perfection, will resemble living beings day by day with this neuromorphic structure. Integrating this system into technology has both benefits and harms. If these are analyzed and managed in the most efficient way, it will break new ground with revolutionary innovations in human life. Thank you for listening.